Brett, if you would like to start sharing your slides, we can move on to your talk.
All right, can everybody see my screen and hear me?
Yes, and
awesome.
All right, so the next talk is by Brett Falk, and go ahead and get started.
Yep, this is joint work with Jerry Tsoukalis and Alon Benheim, and we're going to look at committee-based consensus. And so we saw in the last talk this notion of Nakamoto consensus, where block producers are chosen by a lottery mechanism based on the amount of either in Bitcoin, the amount of hash power they have, or in a proof of stake setting, it can be by the amount of stake they have. And so like blockchains like NXT use this exact mechanism of Nakamoto consensus, where you select a single block producer by a stake-weighted lottery instead of a proof of work based lottery. And in these cases, proof of work and proof of stake are these kind of Sybil resistance mechanisms for using this lottery. But there's a lot of alternative consensus mechanisms that still can use proof of work or proof of stake, but have a different kind of consensus. And so we're going to be focusing here on this type of committee-based consensus. So instead of electing a single block producer who produces the block, and then choosing a chain based on this sort of longest or heaviest chain rule, like it's done in Nakamoto consensus in Ethereum and Bitcoin, you can elect a committee of block producers, and this committee can then run a classical consensus algorithm. And most of these classical consensus algorithms have some threshold that as long as 2/3 of the committee is honest, meaning they sort of follow the protocol or they run the vanilla version of the software they're given, this committee will reach consensus on a single block. And this type of committee-based consensus is used in a lot of protocols. It's used in these delegated proof of stake systems like Tron and EOS. It's used in almost every chain in the Cosmos ecosystem, including the Cosmos Hub. It's used in Algorand and also on the Binance Smart Chain, which is basically a fork of Ethereum that's running proof of authority. And there's a lot of potential benefits of a committee-based consensus. So some of the arguments are that it allows kind of a specialization, that if you elect a committee, this can be a committee where they have good hardware and high network throughput and low latency. And so you can speed up the blockchain a little bit because you have these professional producers. One of the big benefits, though, is that you can get instant finality. So in Nakamoto consensus, you can have basically the chain can fork, right? The consensus is reached by a longest chain rule. And so in Bitcoin, for example, there's a heuristic that you don't consider a transaction finalized until it's buried 6 blocks deep. It's not once you see your transaction in a block, you have to wait for some amount of time until you're pretty sure you're on the longest chain. Whereas in chains with instant finality, as soon as you see your transaction in the block, you can be fairly sure it's finalized. And so these chains that use Nakamoto consensus, right, see a lot of these short-term forks. So Ethereum has basically at minimum about 100 uncles a day, which are blocks that get uncled out and don't end up making it to the longest chain. Bitcoin has many fewer because the block time is much longer, but they still see about 1 uncle per month. And so that's, that's something you have to worry about if you want your transaction to go through. And this is something you can get rid of with these committee-based consensus protocols. And it's a big selling point for a lot of committee-based consensus schemes. One thing I'm kind of interested in is committees can also do other things. If you elect a committee, you can force the committee to all use specialized hardware like Intel SGX, and then you can make the whole blockchain secret. And that's what the secret network does. Or you can force the whole committee to run some distributed key generation algorithm and encrypt their mempool. And so you can have a private mempool and get rid of a lot of the problems of MEV. And this is what Osmosis is planning to do. You can also ask the committee or even a different committee to hold secrets and have private information on the blockchain. And so the Algorand Foundation has a number of papers that outline sort of how you would elect these committees to hold secrets for you. You can ask the committee to be price oracles, so you don't need to have external price oracles. So like Terra, the Terra blockchain, right, their whole ecosystem is based on price oracles because all of their synthetic coins like UST are based on knowing the real-time market price between US dollars and their native token Luna. So they need price oracles. Instead of having external price oracles, they take their block producers to be price oracles. And since you have a committee of block producers, this is a good way to do this. The Binance chain even uses a committee elected on the Binance chain to choose the committee on the Binance Smart Chain. So you can have this committee of block producers control another chain. And so there's a lot of kind of interesting things you can do with a committee that make this type of committee-based consensus fairly appealing, I think. Now, there's the big drawback of committee-based consensus is that these classical consensus protocols require communication that grows quadratically with the number of people in the committee. So if there's n people in the committee, it requires n squared communications. You have to keep the committee size kind of small. So small is relative, and nobody knows exactly what small means. EOS uses 21 block producers. Tron uses 27. Cosmos, most of their chains use 150. Oasis uses 110. The Binance chain uses 11. The Binance Smart Chain uses 21. And the one exception here is Algorand, which does a lottery-based consensus, ends up using a lottery-based committee selection, ends up using a lot more committee members. And I'll talk more about that in a little bit. But this type of small committee, even if you elect new committees all the time, the committee can end up being static. And so you see this really extremely in systems like EOS. So EOS elects a new committee every 2 minutes, about every 126 seconds. And they elect 21 people at a time. In the first 89 million blocks they produced, they only had 63 different block producers produce all of them. And even Cosmos, which does a little better, the Cosmos Hub, had only 215 block producers for the first 9 million blocks. By contrast, right, Ethereum in the first 8 million blocks were mined by more than 5,000 distinct addresses. And Bitcoin, if you count the number of addresses that were paid out to in block rewards, you get up to about 275,000. And so these committee-based consensus protocols are much more centralized than the alternatives. And so this is a big drawback of these systems. But nevertheless, a lot of places use them. So most of the Cosmos chains, including Cosmos Hub, Crypto.org, which is Crypto.com's chain, Terra, the Secret Network, Osmosis, many more, the Binance Smart Chain, Algorand, Tron, EOS forks like Telos. So this is a really widely used method of coming to consensus. And so I think it's important to understand how these work. In terms of this, in terms of seeing hands, I see some hands going up. Should I take those questions now? How do I even get back to that?
I think that's okay if you want to keep going. So I would encourage everyone to put questions in the Q&A. And some of them we can try and answer during the talk if it's a clarification question. But I think typing it into Q&A first would be better. Okay.
Sorry, yeah, I just didn't have the window of participants open to see I just get messages. So the purpose of this talk is to ask basically how you should elect the committee. So first question is who's sort of allowed to vote, and you need some sort of Sybil resistance mechanism. And all the chains I mentioned all use proof of stake as their Sybil resistance mechanism. You get votes proportional to your stake. But in principle, you could do this with proof of work, and people have proposed actually using proof of work where your voting power to elect a committee is proportional to the amount of hashes you do. But that's not what we're focusing on. We're focusing on here on the voting mechanism. How do you elect a committee? So the simplest thing to do is to say you have a single vote mechanism. You get one vote to elect somebody to a committee. Your vote is proportional to your stake. And then you look up at all the candidates and you select the K candidates who get the most votes, and that's your committee. And you run this election maybe every 2 minutes, every 5 minutes, once a day. You get to set that parameter, but it's just a single vote mechanism, and your vote is stake weighted. And this is by far the dominant method for committee-based consensus elections. An alternative method is through what's called approval voting. And I'm going to talk a bunch more about that. But in approval voting, you don't vote for a single person. You approve of any number of candidates that you want, and they all get the full weight of your vote. And at the end, we count up who has the most approvals, and the candidates with the most approvals are elected to the committee. And finally, an alternative method is just a lottery-based mechanism where you just have a stake-weighted lottery, and you choose K people at random proportional to their stake to be on the committee. And so we're going to look at how these different committee selection mechanisms perform. So the main question here is, what's the best way to choose a committee? So let's start with the lottery-based mechanism, because that's kind of the simplest. So in the original Algorand paper, they say, if we assume that 80% of the stake is held by honest people, and we're going to elect a committee of size K, then we can actually figure out what is the probability that 2/3 of the elected committee is honest, right? And that's when consensus will fail. And that's when you could have a fork or a double spend attack, and you would lose this instant finality. And so they can do an analysis. It's very straightforward, right? To say, well, the probability of a random committee of size K being elected and having more than 1/3 dishonest or less than 2/3 honest is the probability of binomial distribution with K samples with probability 0.8 is less than 2K/3. And you can calculate this exactly. And they give some suggested parameters in the white paper saying, we wanted the chance that a malicious committee, a committee that's more than 1/3 dishonest or less than 2/3 honest is selected, and they choose some parameters like 10 to the minus 12. We want this probability to be less than 10 to the minus 12 under the assumption that 80% of the stake is honest. And with this failure probability, if they produce a new block every 4 seconds, so like a new committee, say every 4 seconds, it takes, there's an expected time of 128,000 years before you elect a committee that's 1/3 dishonest, because these concentration bounds are really very strong. Right, the binomial is very highly concentrated. And you can get a nice bound if you just take the turnoff bound, the probability that a binomial where you select n people with probability p, the probability you're more than a 1 minus delta fraction away from your expectation decreases exponentially in the committee size n. And so in this case, if 80% of the stake is honest, so in this case, P is 0.8, then the probability of a dishonest committee decreases like e to the minus n/90. This is an upper bound on this. So you can be sure that you won't get a committee with, a dishonest committee with more than this probability. So it decreases exponentially. So if you make n big enough, you can make your probability of a bad committee go to 0 exponentially quickly. And so this is the determinant. This is how they choose how big their committees are going to be. And one of the arguments for doing this is basically that incentives are really complicated. And so Algorand sort of very publicly adopts this sort of incentive-free design. So there's no rewards for block producers, there's no slashing for misbehavior, and there's no voting because they say it's really hard to design these kind of incentives. And the cost for that is they have to have bigger committees. By contrast, most of these other systems have some method for electing committees. And the main question is, can you do better with voting? Can you basically make the committee size smaller, which would make your whole chain more efficient by having some voting to try to tap into the wisdom of the crowds about how you select committee members? So we model this by saying, basically, you're trying to elect a committee, and there's a binary outcome. It's either a good committee or a bad committee. And it's a good committee if some fraction, say 2/3 of the elected people are honest, and it's a bad committee if less than this fraction is honest. And this is the model that's used in most cryptographic analysis. And this is also the model that's used in most classical consensus protocols, where there's some sharp threshold that as long as more than some fraction, like 2/3 of the people follow the protocol, then you're guaranteed to come to consensus. And below this threshold, sort of almost anything can happen. And in our model, we assume voter incentives are aligned. Everybody wants to elect an honest committee, but they have very little information, right? When you were voting for block producers on some chain like Cosmos, you have very little information about who's going to be a good block producer or not. And to simplify things, we ignore these secondary characteristics about candidates that you might care about, like uptime or latency, right? You would like to elect committee members, not only who are honest, but who are going to be really fast at producing blocks, because again, you could increase throughput that way. But that's not really part of our model here right now. So in approval voting, you get to approve of a set of candidates, and the weight of your approval is proportional to your stake. And then the system aggregates the K candidates who got the most approvals, and they're elected to the committee. And now this is strictly more general than a single vote system where you are allowed to only approve of one candidate. In approval voting, you can approve of any number you want. But one of the drawbacks of approval voting that's been noticed in, a long time ago is that it's a voting system that there's not a unique honest strategy. So even honest voters need to be strategic, and you kind of see this right away. If there are 4 candidates like A, B, C, D, and your preferences are B first, and then A, and then D, and then C, you have to choose. Do you vote for just B, or do you vote for B and A, or do you vote for B and A and D, or do you vote for all 4 of them? And these are all consistent with your preferences, and you have to choose, and your strategy is now going to depend on what you think other people are going to do. And so this is different from like single choice voting, where if you're honest and not strategic, there is sort of a natural, a single unique strategy. So in approval voting, the voter decision process is kind of hard. So here's our model. We have M candidates, and each candidate is honest with probability P, and we have N voters. And each voter receives some signal about the candidate J. So you get some signal Sij star, and it's coming from a normal that's centered around some piece of H for honest producers, and centered at some lower value for malicious producers. And from this, you can calculate the posterior probability that candidate J is honest based on your signal. And so what is a voter going to do? They're going to look at all these signals, these posterior probabilities of voter I has this posterior probability Sij that candidate J is honest or dishonest, or that it's honest. And in approval voting, you get to choose the top Z producers to vote for, the top Z candidates. And in regular single vote voting, you just get to choose, you just choose the top one. So there's no strategy there. But the question is, how should you set this optimal threshold? How many people should you vote for? You see these posterior probabilities, you rank the producer candidates based on the probability you think they're going to be honest. And now how many should you vote for in order to maximize the probability of electing an honest committee? And a big question is this much better than, can you do, clearly in this very simplified model, you're going to be able to do better than single vote voting because it's strictly more general and everyone's incentives are aligned, but do you do much better? And is that worth this extra cost of basically making it unclear what voters should do? So we know that if all voters acted optimally in approval voting, they do better than single choice voting, they do better than lotteries because our model is simple, but it's not clear if they pursue a suboptimal strategy, right? They may actually do worse than single vote voting, or they could even potentially do worse than lottery-based elections. So let's see kind of what happens. So first is, let's look at what kind of strategies could voters take. So we identify 2 types of strategies that are sort of very natural. One is kind of a threshold, we call it threshold voting strategy. You vote for everybody you think has a better than, say, 75% chance of being honest, or better than a 50% chance of being honest. An alternative strategy is a cardinal voting strategy, which is you vote for the top 5 people, or the top 7 people, regardless of what their probabilities of being honest are. And these seem like 2 very natural strategies that people might want to pursue. These are not the only possible strategies. The strategy space is really complicated, but let's look at these to begin with. So in the threshold voting strategy, you just, you get your signals and you have these posterior probabilities Sij, and you vote for all candidates that are bigger, whose probability is bigger than some threshold. And now we can actually calculate explicitly what is the number of votes that an honest candidate gets, and what's the number of votes a dishonest candidate gets. And we can actually calculate this distribution explicitly. And it turns out it's a Poisson binomial distribution. And then we can actually calculate a closed form solution for the probability that a committee of size K is 2/3 honest. It depends on the order statistics of these two different Poisson binomial distributions. So we get a closed form, but it's really, really messy. But we can now plot this. And so this plot shows is not a simulation. This is actually like an evaluation of this closed form. And imagine the single vote setting. And we have a single vote setting, and they're going to choose, they're going to vote for everybody. The x-axis is what their threshold for voting. Here, this is if you vote for everybody you think is a 40% chance of being honest. This is the chance you vote for everybody who has a 60% chance of being honest. This is the chance you vote for somebody who's an 80% chance of being honest. And the idea is there is actually a single optimal here. And it's about 66%. It's kind of what you'd think, that you vote for people who you have a 2/3 chance of being honest. And intuitively, this makes sense. If you vote here, you're voting kind of for too many people. You vote for almost everybody, and you can't distinguish honest from dishonest people. Everybody gets one vote. And if you vote here, you're not voting for anybody. Nobody gets any votes. And again, you can't distinguish, but there's this optimal threshold where you're kind of distinguishing honest candidates from dishonest candidates, and your vote is actually conveying some information. So this looks really good, but the problem is the second you go to 2 voters, now all of a sudden the optimal strategy is not at all clear. Now you have 2 voters. If they both vote for too many people, this is the region where all the candidates essentially get 2 votes. And now here, you get a nice differentiation. If people vote at this level, they vote for people who are 55% chance or more of being honest, then the honest candidates will get 2 votes and the dishonest candidates will get about 1. But if you deviate from this optimal strategy a little bit, you totally kill your chances of electing an honest committee, because now essentially this is the case where I guess everybody is getting 1 vote. The honest and dishonest people are getting both 1 vote. You can't distinguish them anymore. And if you raise things a little bit, then the honest people get 1 vote and the dishonest get 0. And then back down here, nobody gets 0. And so this is kind of worrisome that once you have 2 voters, the optimal strategy is now very, very delicate. If you're off from it, you are in bad shape. And if you have 3 voters, you get 3 peaks. And if you have 4 voters, you get 4 peaks. The one nice thing is once you get a lot of voters, the peaks kind of merge. And so here's what happens with 100 voters, that the strategy already now is becoming like pretty robust, that if you follow a threshold strategy, you have a really high probability of electing an honest committee, essentially no matter what you do. So this is kind of nice. And this is sort of what you would hope for, that these strategies would be robust because they're very hard for voters to calculate. So let's look, what if people follow the cardinal voting strategy, where you vote for the top candidates regardless of what their signal is? There's some evidence. We scraped votes off of EOS where they do approval voting, and it looks like people are following these kind of threshold voting strategies. So there's spikes here. This is the number of people you vote for. There's spikes at like 21, but the committee is size 21. So a lot of people, I think if the committee's size is going to be 21, I'm going to vote for 21 people. And EOS imposes this arbitrary threshold that you can't vote for more than 30 people. And a lot of people just vote for 30. They say, I'm going to vote for the maximum. So it seems like people are maybe following this this cardinal voting strategy on EOS at least. And the nice thing is we can show if there's only 1 voter, or if all the voters pool their information, cardinal voting is indeed optimal. This is actually strictly better than threshold voting. And again, these aren't simulations. These are the actual probabilities in the case that you have 1 voter, that when the committee size is 21, you get all of these things have peaks at 21. Unfortunately, once you have more than 1 voter, cardinal voting is no longer optimal. And it's almost impossible to find optimal strategies. But you can simulate things. And so we were trying to look, one of the big questions here was about, is approval voting basically better than single choice voting? These are the 2 sort of dominant ways that people are electing committees. And so we can imagine, suppose all voters followed a cardinal threshold. They vote for the top 1 candidate, top 2, top 3, top 5, top 10. And here, right, we see this is what happens when people vote for 1 candidate. So this is like single vote elections. And this is the probability they elect an honest committee. And these are the lowest. And these 2 lines represent basically how much information candidates have, right? So in the green things, voters have more information. In the purple, they have less information. But in both cases, right, we see that single vote voting is the worst of all approval voting. It's better if you let people vote for 2 people. It's better if you let them vote for 3. It's better if you let them vote for 4. And it tends to get better. And this horizontal line is the probability of electing an honest committee. So we have the a priori probability that somebody who's honest in this plot is 75%. And so if you elect a random committee with people of 75% probability, what's the probability 2/3 of the committee is honest? It's about like 75%. Here it's like, and so this is fixed. It doesn't depend on a voting strategy. Right? But this is already interesting because now we see like, it looks like approval voting, even if voters have very, very little information, is better than single choice voting. And if you increase the committee size, so that was with committees of size 21, which is like what EOS uses, and what BSC uses, and here's committees of size 150, which is what Cosmos uses. And so all the probabilities go up. You're much more like, the bigger the committee, everything goes up. The probability of randomly selected committee is 2/3 honest, is already now almost 99%. But we still see that single vote voting is basically the worst of all of the approval voting options, even with these kind of larger committees and with voters having very little information. So one of the sort of take homes from this is all of these methods converge exponentially quickly, even lottery-based consensus. They all converge exponentially quickly. And in approval voting, even though you can't figure out what the optimal strategy is, the approval voting is actually very robust to sort of almost any strategy works very well. But even with suboptimal strategies, like we know that voters following a cardinal strategy is suboptimal. There's some strategy they could use that's much better. But even with these suboptimal, very simple strategies, you end up with systems that are actually much better than just single choice voting. And so sort of moving forward, right, there's lots of other election mechanisms that we haven't thought about at all, right? We focused on approval voting because that's what's being rolled out in some of these things, but you could use quadratic voting, you could rank choice voting, there's many others. And it seems important to figure out, how do you want to elect these committees? Because this can be sort of divorced from all the other aspects of the system, right? You can choose these systems have different virtual machines, right? Binance Smart Chain uses the Ethereum virtual machine, Cosmos uses CosmWasm, right? Like you don't have to focus on this. You can change your ideas of block rewards, but this question of how do you sort of elicit information from the users about how to select a committee seems really important. And it can be sort of tweaked independently of all of the other aspects of the system. And another thing we'd like to sort of do moving forward is, right, make the model richer. Right now, all of our voters, their incentives are aligned. They want an honest committee. But what if some fraction of the voters are malicious, or some fraction of the voters really care about performance? Or if there's vote buying, this is actually a topic of discussion. There's lots of vote buying on these systems. It's very easy to set up contracts where you can pay people to vote for you as a block producer, and then you can share your block rewards with them. And so this type of vote buying is really prevalent in these systems. And how does that change things? So I think a really interesting question. So thank you.